Welcome back. Another day, another lecture. This one is the second half of lecture 10. And in this one, we're going to take the plunge into the phenomenon of galaxy mergers and interactions. We will be looking at some pretty cool pictures, as you can already see here, but we are also going to be looking at some pretty cool physics. Let's just start by appreciating how immensely cool interacting galaxies can look like. I don't really have any other reasons to show you this picture than just to go, wow. If we try to zoom in a little bit on the central parts, this is like really detailed and really high quality. We can see how this galaxy has kind of plunged through the larger major spiral galaxy. We can see that the smaller one also seems to be a disturbed spiral. We can see how its gravitational interaction has pulled these like strands of dust and gas with it coming from the disk of the larger spiral. We can also see the disturbed and broader orbits of a halo of stars that is kind of following or forming around the smaller galaxy. We can even see kind of a bridge of stars between these two galaxies, and we can see that especially the smaller galaxy is very blue, probably due to a very recent intense bout of star formation that has been sparked by this interaction as well. This is so cool. I don't know what more to say about it. So that's why I wanted to show this to you. You can pause it now and just sit and gape a little bit at it before we continue in this video. Okay, assuming you're all done going ooh and ah about the last picture, let's take a little bit more of a theoretical look at galaxy interactions. So the effect of interaction on a galaxy depends a lot on the orbital parameters of the interaction, and it depends on the internal properties of the systems. So the orbital parameter can be the relative speed, like how rapidly they are zipping past each other. The impact parameter is the distance between the two galaxies at the closest passage. Either they can have a large impact parameter where they will never collide completely, but will only get close to each other, or they can have a very small impact parameter, which leads to a direct collision, or anything in between. And the internal properties of the system, which is mainly the density and velocity distribution, but also the gas content, for example, will have a very strong influence on how these galaxies will react to an interaction. There are three major classes of interaction. One can say the first one we will look at is what we call major mergers. These ones are when two galaxies of roughly equal mass are merging, for example, the antennae galaxies that we have looked at before. Then there is a minor merger, that is when a satellite galaxy merges with a large host galaxy. For example, with the Milky Way, which has the Sagittarius dwarf spheroidal merging with it. And probably the Milky Way has been swallowing up other dwarf spheroidal Sagittarius or dwarf spheroidal satellite galaxies for breakfast quite a few times in its history. And finally, there are what we call flyby interactions, which are the largest impact parameters where galaxies are passing each other at larger distances or large relative speed. These have more moderate disturbances than mergers. They will definitely ruffle the hairs of the galaxies that are involved, but they will not be completely destructive the way a major merger can be. Here's another cool picture, just because I thought that we deserve to get to look at some really cool pictures when we are talking about something as dramatic and like theatrical as galaxy mergers. This is the merging pair called Arp Madore 417391. I don't know much about it, but you can see how you have two core spiral galaxies which have merged. You can see how you have like these streams of stars that have been flung out, and how in parts of it, it has sparked intense star formation episodes as well. And you can even see that there's a stream of older stars being flung out in the opposite direction. Mergers can happen between two or more galaxies, and major mergers can also be of more than two galaxies, but they are quite rare. On the other hand, when two large galaxies are colliding in a major merger, satellite galaxies are almost always involved. So in that way, you can say they are still kind of a multi-galaxy event, but there will be two major galaxies in such a case, and a number of satellites rather than a larger number of major galaxies. So there are two very different kinds of mergers when we're looking at major mergers, and they are determined very strongly by the gas content of the galaxies involved. So they behave very differently depending on whether they're gas rich or gas poor. So we distinguish between what we call dissipative or gas-rich, or sometimes wet mergers, where energy can dissipate via the collisional and radiative cooling of the gas, and what we call dissipationless or gas-poor or dry mergers, where only stars and dark matter and perhaps a little bit of very hot ionized gas is present, where there's no energy dissipation, and that leads to some very different results. Here we see an example of a couple of gas poor or dry mergers, which are observed with the Hubble Space Telescope, I believe, back in 2005. And here we have our example, the well-known antennae galaxies that we have looked at before. Here we can actually see them at a larger distance than we looked at earlier, where we can see that there is the core we've been looking at, where the two galaxies are merging and have sparked a galaxy-wide starburst event. But you can also see the large stellar streams which have been flung out from these galaxies and which have given this galaxy pair, or this forming megagalaxy, its name. But let's try and take a look at the actual physics of mergers. Mergers are super complicated, and we cannot get super detailed about it, about the formalism of it, but we can definitely take a look at some of the principles of physics involved in mergers. So in smaller systems with lower internal velocities, the system merges through what we call two-body relaxation of the stars involved. For this kind of galaxy mergers, the time scale for virialization, that is for the stars to settle into an energy equipartition equilibrium where the virial theorem is valid, that time scale is larger than a Hubble time. So we would not expect to see a lot of virialized galaxies in the universe, but we actually do see quite a few of them. And that's because virialization also can happen through other mechanisms than just the two-body relaxation. So it can happen through what we call collisionless relaxations, such as the so-called phase mixing, and perhaps my favorite astrophysical expression of all times, violent relaxation. So this can allow us to estimate the merging timescales for major mergers. In particular, violent relaxation can actually shorten the timescales for virialization of early type merging galaxies quite dramatically. For minor mergers, the effect of the host and the satellite can be described through effects such as tidal stripping and dynamical friction. And dynamical friction is a quite important phenomenon, so we are going to now dedicate a little bit of time to that. So what is dynamical friction? Dynamical friction is an effect of a scenario where a large mass, such as a satellite galaxy, is moving through like a sea of much smaller masses, such as stars, for example, a satellite galaxy moving through the stellar disk or the outskirts of an early type galaxy or the stellar disk of a spiral galaxy. And so the gravitational pull of the smaller masses on the large one will result in a change of orbital velocity, which is given by this formula here. Lambda is a function that depends a lot on the specific setup of the system. It depends on the distance of the closest approach. It depends this function f, or this factor f, depends on the velocity dispersion of the small particles, and the velocity change is directly proportional to the mass m of the large mass. So dynamical friction depends on the velocity, so at slower passage there will be a stronger deceleration, simply because all these masses here will have a longer time to exert gravitational acceleration on the larger mass. It also depends on the satellite mass. If the satellite has a larger mass, it will also lead to a stronger deceleration. And finally, it will depend on the halo mass density, so the mass density of this sea of stars, as we can look at like before. So higher density also means stronger deceleration. But given that slower passage means stronger deceleration, that also means that as this effect has time to work, it also starts working more and more strongly. So the more a satellite galaxy or a similar mass has been slowed down already, the more efficiently the slowing down will work and deprive it of its remaining velocity. So in that sense, it is very similar to how static friction works, and that's where it gets its name from. So if we are looking at these figures over here on the right side, we can get an idea about how it works. So that if this satellite is moving through this sea here, you can see that it exerts a gravitational pull on the nearby small stars, so that they will all be pulled towards this line that the mass is moving along. And these will then be concentrated in the wake of the larger mass, but that also means that the mass concentration of these will be larger. The mass density along this, like behind the satellite galaxy's mass, will be larger, which will lead to a stronger gravitational pull on the satellite mass. And a lot of that kinetic energy that it loses will be converted into a larger velocity dispersion of the stars in the galaxy. So basically, such a mass, as it moves through this sea of stars, it will kind of be stirring the pot, leading to a larger dynamic, to a dynamic heating of its immediate surroundings, to a larger velocity dispersion than there was before. And in order to do that, it needs to deposit a large part of its own kinetic energy into this randomized kinetic energy of the sea of stars that it's moving through. So we can think about what these dependencies mean for the merger timescales of larger spirals, such as the Large Magellanic Cloud or the Small Magellanic Cloud with the Milky Way, in comparison to, for example, globular clusters. I think we will take a little bit of time discussing that once we meet. Tidal interactions are when satellite galaxies are passing close to a larger system, but not necessarily as merging with it. So these can be like the results of flybys, or what we also call harassment sometimes. So a satellite passing close to a larger system loses material to the larger system if its gravitational pull becomes larger than that of the satellite within the satellite itself. Okay, we'll take a look at that. If we look at the figure over here, we can see that we have a satellite and we can see we have a larger mass host. So if the larger gravitational pull of the host becomes larger than the gravitational pull of the satellite inside of the satellite itself, then the host can start pulling material off the satellite and onto itself. The point where these two gravitational pulls is equal is called the rho slope, or the rho radius, or the Hill radius, and it is marked by the two Lagrange points L1 and L2. But that means that once a satellite is moving closer to a larger galaxy and this Roche limit is surpassed, then the larger host can start picking material off of the satellite, and that will lead to tidal stripping, and that will lead to tails developing. So that is when we get these large tails of gas, and sometimes also of stars, that we have seen, for example, in the Magellanic Stream. That was it for today. Now remains only the discussion questions. Discussion question A says, what affects whether a galaxy loses its gas in an interaction with its environment, for example, a close encounter with another more massive galaxy? And B, the local group contains the galaxies closest to us. Discuss what observations and analyses could be made on these galaxies that are nearly or fully impossible to obtain from more distant objects. Are there any caveats with these studies? Are there any ways that such studies could be, let's say, problematic, in the sense that we maybe couldn't directly transfer what we have learned from the local group to more distant galaxies? I am looking forward to be discussing this with you all next time we meet. This was all for lecture 10, and I will see you in the next one.